All right, we're gonna try this out. I'm gonna try to speak loudly so that my microphone on my cell phone picks this up. And I'll try to write big on the whiteboard so that hopefully you can see everything I'm writing down. Anyway, let's get to it. So today we're covering 5.5, which is about double angle identities. So double angle identities. So without any ado whatsoever, actually, let me say this. So let me show you what it is that we're working on. I'll stand behind the camera so that I can make sure that you can see what I'm pointing at. So we're going to be looking at the double angle identities here, okay? And I'm going to prove this first identity to you, that cosine 2 theta is cosine squared theta minus sine squared theta. I'm not going to prove any of the rest of them because they're all kind of similar. The proofs of these things are all similar. But what you will notice is that for cosine 2 theta, we have 3 different identities. For sine 2 theta and tangent 2 theta, we have one identity each. But, you know, that's just because these things are going to be useful at different times in different circumstances. So we're going to talk about those guys. Then the other thing we're going to talk about are these product to sum and sum to product identities. I'll prove one of these things to you, not going to prove all of them. And I'm honestly not going to emphasize these very much. So, but, you know, they're on your list of identities because they are, you know, fairly common ones that you see occasionally. So anyway, but the main topic of discussion is these guys, the double angle identities. Okay. Well, that works out pretty well, rather than using a dot cam, I guess. Double angle identities. So I'm going to prove the first one to you. So cosine 2a is cosine squared a minus sine squared a, which is kind of nice. Cosine squared plus sine squared is 1, right? Now you know cosine squared minus sine squared is cosine of double the angle, right? So that's kind of nice. Anyway, it's a short proof. Okay, so the way we prove it is we say, we've kind of seen this trick already, but we're going to say cosine 2a is cosine of a plus a. And then we can apply one of those sum identities for cosine, and we can say, well, cosine a plus a, that should just be cosine a minus, because the sign changes when you're dealing with the cosine, right? Minus sine a, and there it is, right? Cosine squared a minus sine squared a. Okay, so that's it for that one. The other two identities for cosine just come from Pythagorean identities. Like, if you replace cosine squared a with 1 minus sine squared a, then you see that this is equivalent to 1 minus 2 times sine squared a, right? Which is one of the formats of the cosine 2a of the double angle identity for cosine, right? It's one of those formats. Same thing if you replace sine squared a with 1 minus cosine squared a. Well, then you see that this is equivalent to 2 cosine squared a minus 1, right? Okay. The other ones, like sine 2a, you prove it the same way, right? You say sine 2a is sine of a plus a, and then apply the sum formula that we talked about last week, right? Last time that we were face to face. Same way with tangent to A. You just call it tangent A plus A. You know, apply the formula, and there we go. So that's the double angle identities, right? So that's how the double angle identities work. I'll give you some examples of these things in action. I just wanted to show you one of the product to sum formulas. Again, I'm not going to show all of them to you, and I'm not really going to emphasize them that much, but I did want to prove one of them to you at least. So here's a product to sum. Okay, so if you ever have a scenario where you're multiplying the cosine of two different angles together, it may come in handy to rewrite that as a sum instead of as a product. And this is the identity that allows you to do that. You can also go backwards, right? As you can see on your list of identities, right? You can go the other way around with this. But let me prove this one to you. So I'll prove this one to you, and the proofs of the others are similar, okay? But they also come from that sum formula. What did we call those? Yeah, the sum and difference identities. Yeah, this also comes from a sum and difference identity. I'm actually going to start with the right-hand side and show that it's equivalent to the left-hand side. So starting with 1/2 cosine A plus B plus cosine A minus B. That's equivalent to 1/2 times. Now cosine A plus B, I can apply a sum identity, and I can say, well, this should just be cosine A, cosine B, minus, okay, sine A, sine B. Okay, so that's all just that first one there. Okay, the second one I can do the same thing. I can apply a difference identity. So I can say this is plus, the second one's going to be cosine A, cosine B, plus sine A, sine B. My parentheses are all lopsided and stuff. I guess I could make this one the same size as the one on the left. Anyway, but now we just combine like terms, right? Cosine A, I have a cosine A, cosine B here. I have another cosine A, cosine B there. So that makes 2 cosine A, cosine B. And then I've got a negative sine AB, negative sine A sine B, and a positive sine A sine B. Those are going to cancel, right? So this whole thing just collapses down to that. And of course, 1/2 times 2 is just 1. So this is just cosine A, cosine B, as desired, right? So there you go, product to sum formula. They could come up, they could come in handy. I didn't want you to get through a trig class without having seen them at least once, but I'm just not going to emphasize them very much, okay? The reason I'm not going to emphasize them very much is because I don't think they come up in calculus all that much, to be honest with you. Could be wrong about that, but I really don't think that you'll see them again, probably, unless, you know, I mean, I could see how this could be useful in some kind of like electronic engineering or something like that. But you're probably not going to see them again for a while anyway. So that's that. Let's go through a few examples. to show you these things in action, specifically the double angle identities, because these things are the most important part of this, this particular section. So, so I'm going to give you one example. Walk you through one and then let you work on one yourselves. Actually, I guess since these are videos, I'm just going to work them all out, you know, just straight away. If you want to try these on your own, which I would encourage you to do, you can just pause the video, right, and try to work it out yourself. Okay. So given cosine theta equals negative 12/13 and sine theta greater than 0, let's find the following. Well, first of all, let's find sine 2 theta. Okay, so sine 2 theta. If you look at your double angle identity for sine 2 theta, then you see that sine 2 theta is equal to 2 sine theta cosine theta. Cosine theta we already know, right? So this is negative 12/13. Sine theta we don't know, but given these two pieces of information, we can figure out what sine theta should be. In fact, if you know your special triangles really well, then you might know that this thing is going to correspond to a 5, 12, 13 triangle. And since sine theta is positive, you can kind of see right away that sine theta is going to be 5/13. In case you don't know all those tricks or have all that stuff memorized, here we go. Let's figure it out. So sine theta, if cosine theta is negative and sine theta is positive, then if cosine theta is negative, we're either in quadrant 2 or quadrant 3, right? That's where x is negative. If sine theta is positive, that means we must be in quadrant 2 then, right? So there's theta. And cosine is adjacent over hypotenuse, right? And then we can solve this. We can say, all right, so x squared plus y squared equals r squared. 144 plus y squared is 169. Y squared is 25. Y is plus or minus 5. And you can tell it's got to be a positive 5 since we're up here in quadrant 2, right? So y has to be positive. Okay, so sine theta should be 5/13, right? So coming back over here, we can say, all right, so sine 2 theta is 2 sine theta cosine theta. This is going to be 2 times 5/13 times negative 12/13. Oh, my calculator is somewhere over there. Nothing cancels though, right? So I guess we get what? 60 times 2 is 120. So this is negative 120 over 169, which isn't going to reduce anyway. So that's our final answer. Okay, so there's that one. Man, it's really hard for me to not ask you if you have any questions. But anyway, there's that. So let's do another one. Let's do cosine 2 theta. So same problem. Let's do cosine 2 theta. Well, we have 3 different identities that we could use for cosine 2 theta. If we only knew let's say that we only knew what cosine theta was, right? Well, so then we could use the version of the formula that only uses cosine theta. If we only knew what sine theta was, then we could decide to use the formula that only uses sine theta. In this case, though, we've already done the groundwork so that we already know what sine and cosine both are. So it doesn't really matter. I mean, I think we can use any of the three formulas and they're all probably equally easy to use. I'm just going to use the one that we proved and say, all right, this should be cosine squared theta minus sine squared theta. I know that cosine is negative 12/13, so this is negative 12/13 squared. And sine theta is 5/13, so this should be 5/13 squared. Okay, so that's going to give us 144 over 169 minus 25 over 169. So what is that? 119? That seems kind of weird. 119 over 169. I can't subtract very well. I know 144 minus 24 would have been 120. So minus 25 would have been one more than that. So bring this down to 119, I think. Okay. So 119 over 169. Yeah, I don't think that's going to reduce. Well, it's definitely not going to reduce, right? Okay, so there's cosine 2 theta. We can also do tangent 2 theta. One way that we could get tangent 2 theta is to use the identity listed on your page. And honestly, I don't have that one memorized. It's like, yeah, 2 tangent theta minus, or over 1 minus tangent squared theta. We could figure that out pretty easily because we did that work over there with the right triangle. So it wouldn't be too hard for us to figure out what tangent theta is to use it in that formula. But I think we have an easier solution here because we already know sine 2 theta and cosine 2 theta, right? So we can just say tangent 2 theta is sine 2 theta over cosine 2 theta. So that's going to be negative 120 over 169 divided by 119 over 169. We can flip and multiply, right? Negative 120 over 169 times 169 over 119. The 169s cancel, thank goodness, because otherwise we'd be getting huge answers. But this is negative 120 over 119. I got scared for a second because I forgot that we were doing tangent, and I was thinking, wait a second, that's less than negative 1. That would be a problem if we were computing sine or cosine, right? Because sine and cosine have to live between negative 1 and positive 1. But this is a tangent value, so it can be whatever it wants to be. Anyway, so that's the tangent value there. Okay, I'm going to start a new video so that it doesn't take 4 hours for this video to upload to YouTube. So we'll continue this discussion in our next video.